All right, class, we're gonna get started. Okay. Just one announcement before we get moving. The homework will be going out on Friday. It's gonna be due the Wednesday after break. I did early in the semester and on the syllabus promise you'd have at least a week to work on any homework. So you'll have more than a week to work on this one, even though I'm not gonna get it out today. There's a request to put out to make the homework from today, not cancel it, but make it due on Friday. Yeah, are there any objections to that? I mean, I don't know if you were working really hard to get it done on time and you feel like that's it. Okay. I'll make that homework due on Friday. Sorry for not doing that sooner so you could focus more. Okay, any other questions or anything before we get started? Okay, great. So today we're going to pick up where we left off. We're in chapter 5 on dimensional analysis. We were talking last time about how we can take just a known functional form, right? So if all we know about some kind of really any physics problem, here we're going to talk about fluid mechanics, but it would hold for heat transfer or mass transfer or anything else. And if all we know is the functional form, as in just the variables involved, we can use the known dimensions of those variables to actually derive a set of parameters, a set of minimal parameters that define what's going on in the function, right? So we looked at an example which was drag on a smooth cylinder, and we saw that we could reduce the number of variables from 5 down to 2, and end up with basically the form of drag relationship that you'll find in textbooks, and that allows you to take, in this case, data from many experimenters over many decades and put it all into a single place, right? Plot this all as a single line. Right? We learned that this is why when you're looking at empirical relationships or you're looking up some coefficient in this class or another one, you generally have some equation versus some equation in engineering. It's not one variable versus another. It's some equation, right? There's some equation for CD, some equation here for Reynolds number. That's because these are generally, when you see a plot like that, these are non-dimensional parameters, and we're plotting one versus the other as a result of a dimensional analysis. And this captures a wide range of different behaviors. I mean, these different behaviors cause the line to wiggle and move around, right? So when we talk about drag, we'll talk a little bit about what's going on here and what's going on here. It's kind of interesting. But the fact that there is one line is what we can develop from dimensional analysis. Okay, but there is some ambiguity, and we talked about this a little bit last time. And this is, I want to highlight and head straight for the ambiguities that arise when we're talking about these things, because they can be confusing if you're seeing them and you're not expecting it. I think that maybe they can still be confusing. Apologies for that, but at least you'll know what you're heading into. So one bit of ambiguity is what do we choose as primary quantities, right? We said, remember, if we have our list of variables, we look at the number of dimensions or fundamental physical quantities that we have to deal with in the system, like mass, length, time, and we choose the same number of primary variables as there are fundamental dimensions. But now the question is, what should we choose, right? We have some rules, we have some guidance, but it's not going to tell us, generally it's not going to, generally there's going to be more than one choice. This is again kind of one of those dark arts of dimensional analysis, because these, depending on which variables you choose, you can actually get very different pictures of what's going on within a problem. So this is an example in your book for really just looking at like the position of a falling object as a function of time. Right, so a relatively simple, or at least a physics problem that you should have seen in earlier class. So not even a fluid mechanics problem. And they go through the example of choosing different primary variables to describe the problem and deriving a set of different coefficients or different pi groups to describe the problem. And each one of them tells you something a little bit different. They're all true. They're all correct. But they just, each one of them just gives a slightly different picture of what's going on. So yeah, so there is ambiguity in what you choose in pi groups, but in a sense, all these different answers are correct if you're trying to find pi groups that describe the problem. Yeah.
So, this question, sorry.
No, it's fine.
When we look at these graphs, are we actually trying to use like the relationship of pi groups to understand the situation?
So yeah, so I'm just I'm referring you to something in your. We're not going to go through this example in depth in class, but these so in the example in your textbook, I just want to highlight the ambiguity that's here that we discussed last time. So the pi analysis, right? The dimensional analysis will tell you what these groupings are, right? So in this case, you have S triple star, T triple star, because this is the third time that they ran through the problem, right? And these were the pi groups that they got. And then these curves are from the known solution, right? So they chose a problem where there's a known analytical solution, right? Just like a falling ball. And so then they plot these curves. They plot these curves from that known solution, if that makes sense, right? So that's so that they know the shape of these curves because they know exactly what the solution is. Does that make sense? Okay. But I mean, just in general, we can see that. So they've chosen. They have different primary variables that they've chosen, so they get different definitions of this dimensionless position of the falling object, and different variables for dimensionless time. And we can see just qualitatively different behaviors, right, for all of these different curves for the four different solutions that they plot. But all of them are correct dimensional analysis, right? So it just gives you a different picture, a different window into what's going on. So I mentioned that, generally, like if we choose a distance, a velocity, and a density as our primary variables, that's going to be very often be a choice that we make. And if we have a viscosity, then Reynolds number is going to pop out, right? But depending on what primary variables you choose, you might not get a Reynolds number appearing as one of your dimensionless quantities. That's fine, right? But it's probably going to be a little different than what you would see in a textbook or something, or in literature describing a problem. And you'll see on the homework an example from last year's exam of dimensional analysis and finding pi groups, where there were something like 19 sets of correct answers to the problem. Made it really challenging to grade because I had to be on the lookout for up to 19 different sets of correct answers to the problem. But all of them were correct, right? All of those, any of those sets of answers were correct, for the problem as I posed it, for dimensional analysis. Okay, so so another way that we can find pi groups is if we know the equation, right? So everything that we have discussed so far was if we don't know the equation, we just know the variables, then we can find pi groups using just the dimensions of those variables. But oftentimes we do have some kind of an equation to start with. This can come from a manufactured data sheet, right? It can come from your textbook. It can come from some kind of a empirical relationship that you've derived. Like, let's say you've gotten a little bit further in your analysis of drag on a cylinder or something, and you have some empirical curve fit to what that equation looks like. You can do dimensional analysis on that. And we can find pi groups from those equations as well. One of the key things that we have to do here is choose what we call a reference scale for each variable in the equation. So for example, if we have V, the velocity within the problem, we would want to choose some reference scale u, right? Some reference velocity that is like one of the important velocities in the problem. So we then would rewrite this. We'd say, we would then express this as v star, where v star is a non-dimensional variable in the problem. It's equal to v over u, right? It's equal to the dimensional variable over this reference scale. So if we're considering flow in a pipe or something, this reference scale might be the mean velocity in the pipe. Yeah. It's like the fraction of some other flow. I mean, this u doesn't have to, like, this number doesn't always have to be less than 1, so it's not really a fraction. But we're now, yeah, we're going to take this, all of the variables. In this case, we're taking velocity, right? So we're starting with velocity. And we're saying how much bigger or smaller is the velocity than some reference scale in the problem. So when we look at flow around an object, right, we'll see how the velocity varies as we get closer and closer to the object surface where the no slip condition holds, right? So if we have flow over this table or something, we'll in chapter 7 look at how velocity varies as we move closer and closer to the table where the no slip condition holds. But we would choose the reference velocity as, for example, the velocity far away from the surface in that kind of a problem. So we're going to take all of our variables and do this. We're generally going to choose physical constants as their own scale, or we're not going to take our physical constants and put them into non-dimensional form. So like mu and rho, we're going to leave hanging around within the problem. And then we're going to take a set of equations. So for example, but we're going to look at the Navier-Stokes equations today. And we will apply this concept of non-dimensionalizing each variable in the problem by a reference scale. So we'll end up with a new form of this expression. And then we're going to manipulate it, right? We're going to divide through by different variables or multiply through by different variables in order to get to a form of this expression where every term is dimensionless. Yeah. V star up there would not be a pi group. This is now a non-dimensional variable. That's right. We're going to see pi groups are going to come out of this analysis, but we wouldn't call that a pi group. Yeah, not in the sense that we defined previously. All right. So one thing that I think some of the questions are getting at, and one thing that comes up here, another ambiguity, is what do we choose for that reference scale? Hold on, I'm skipping ahead on my slides. So here in Navier-Stokes, we're going to choose a reference velocity u, and we're going to have to choose some reference length L, because we have all of these derivatives, for example, are with respect to length. And so we're going to have to choose a reference length L in order to non-dimensionalize this expression, which we're going to start on just another slide. And viscosity and density are going to be constant. But so there's more ambiguity here in dimensional analysis, which is what do we choose for our reference scales? So an example would be the length for scaling flow around an airplane, right? Let's say we want to figure out what the flow looks like around an airplane. We're using Navier-Stokes to solve this aerodynamics problem. Like what length should we use? Anyone? What length would you use here? What's that? 1 meter. So 1 meter doesn't actually tell us anything about exactly what's going on in the problem, right? So actually, that's an important point. So thank you. The reason we're doing this, right? The whole reason that we're doing this kind of a scaling thing is that and I alluded to this, maybe on the first day of class or something, but it's worth bringing up again now. The physics of what's going on for flow around this airplane or flow out of this air conditioning duct that won't be quiet doesn't care, right? In a real sense, doesn't care. Maybe not in a real sense. It doesn't care about the length of a meter, right? That is not a relevant length scale for what's going on as air encounters an airplane wing. So that doesn't dictate the physics of the problem, right? The length of a silver rod in Paris, right, it does not dictate the physics of what's going on when air encounters an airplane, right? So if we're looking to compare, a larger or a smaller airplane to each other, those might have some substantial difference, right? Those might have some difference, model airplane versus a really large one. And so a more relevant length scale is something that's internal to the problem. So we want to choose our reference lengths and our reference velocities as quantities that are kind of internal to the problem, that help define what's going on in the problem. So another idea for what we can use for a reference length, yeah, so the wingspan, right? We could try to choose something like the wingspan. I mean, and you can choose, right, or overall length, I think was the first one that I wrote down. The wing chord, right? So this is called the chord of the wing, but like how wide it is, kind of. That might be a useful thing, but you can see that varies. The wingspan, the body width. So this is the ambiguity, though, is what do we choose as the length scale to analyze this problem? And the answer is that we have to consider what it is that we want to analyze, right? So do we care about flow around the wing, right? If we care about flow around the wing and flow is coming in this direction, then one of these lengths is probably going to be a pretty good scale. Because if we have an airplane that is, 10 times smaller, right, or has a wing that is 10 times narrower, then we might expect there to be different behavior than if that wing is, the size of a 737 or something. So that length scale, right, like this width of the wing, how wide or narrow the wing is, tells us, is going to change the solution to our equations. It's going to change the way that this system behaves. And if we choose something like a unit of measure, right, like a meter or something, then it's not telling us about what's going on within this particular problem. It's not going to be responsive to what's going on within this particular problem, if that makes sense. Okay, so we want to choose our reference scales as quantities that are related to the physics that we're trying to solve, right? So we're going to consider what we want to analyze: flow around the wing, flow around the body. And what we're going to see is that in some cases, the reference scales that we need to use are kind of predefined. Like if we're considering flow in a pipe, we're pretty much always going to use the diameter of the pipe as our reference scale. But in general, if we just want to get an idea of what's going on in the problem or do a dimensional analysis, and then a lot of times all we really are going to care about is the order of magnitude of all our different variables, as in like what power of 10 are they? And so in practice, pretty much any length you could pull out of this airplane would probably work for a scaling analysis of flow around the plane. Okay, so I saw some puzzled looks and maybe hands about to come up. But yeah, go ahead. Yeah.
So if you want to do, for example, like the actual plane, would it be reasonable to like break them into pieces and have their own like individual dimensional like schema factors for each piece?
Interesting. Yeah. So the question is, if we wanted to analyze flow around the plane, would we break it up and use different scaling factors for different pieces? No, I think you'd still want to use a single scaling factor to describe the whole problem. If you had some expression describing flow around the airplane or something, you probably would just use a single scaling factor for the whole problem. Yeah, that's a good question though. Yep.
There's a reason for doing the reference scale, just that way it's easier to scale it up and down. How we're analyzing that. With the situation that like scale up and down relatively freely.
It's so the question is it so that we can scale it up and down relatively freely? That's part of why we do it, and we're going to talk about how we can use dimensional analysis in that sense of how we can understand what's going on in a model situation and know how to apply that to like a real, let's say, much larger scale situation. So that's definitely one reason why we're going to do this. But I think the the more important reason why we're going to do this, which we haven't discussed yet and we're about to get into, is that by choosing the reference scale as something that is relevant to the problem, we're going to, from equations describing the problem, like from the Navier-Stokes equations, we're going to derive non-dimensional parameters that define the physics of the problem. And then those non-dimensional parameters will tell us, so we said early on that, like first day of class, that non-dimensional parameters are basically the ratio of one thing to another thing. Like the Knudsen number is the ratio of the intermolecular spacing, right? The space between individual molecules, and the length scale that we're considering in the problem, right? So let's say the length scale is like the width of an airplane wing. The Knudsen number would be tiny, right? Because the space between air molecules is much, much smaller than the size of an airplane wing. And so that dimensionless parameter tells us that the space between molecules, it's so small relative to the size of the thing you care about that you can ignore it, right? And so when we do this kind of scaling to a problem or to an equation, then we're going to see some dimensionless parameters, pi groups, pop out that will tell us about which pieces of the problem are important and we have to consider, and which pieces of the problem are not important and we can ignore. Okay, so yes, and we are going to talk about modeling, which is about scaling things up and down, but it has more to do with like what are the relevant physics. Okay, is okay, yeah, and we're going to see this through some example of applying this technique. So this is so if we look at our Navier-Stokes equations and we take this concept of reference scales, we said that we're going to have reference scales for velocity, for length, and then we're also going to consider the density and the viscosity of the fluid. And then we can go through and write dimensionless forms of every variable within the problem. So for example, the velocity, like this case is vector velocity v, would be scaled as vector velocity v over this, whatever this velocity scale we choose for the problem is u. That means that each component of velocity, right, the x, y, and z component, they're all being scaled by that same reference velocity in this problem. All of our like x, y, z variables, they're going to be scaled by L, our reference length in the problem. Time, we can take, so we didn't put a reference time into the problem because we can take L divided by U, length divided by velocity, to get something that has dimensions of time or that tells us about characteristic time in the problem. And so we use that as our reference scale for time. Our operator, you notice is written up there as L times V, sorry, L times del. And that's because if you remember, the del operator has X, Y, and Z in it. And so we have to make sure that we scale that operator as well. And for the pressure, we're using a pressure scale that we can again derive from the fundamental quantities that are in the problem. In this case, rho u squared will give us a something with dimensions of pressure. So we're going to take this and we're going to apply this new definition to all the variables in the problem. Yeah.
So when we're choosing like how to represent, should be primary groups, or we only have like that many case with reference, you know, that we're using just that way we don't like throw out a whack and choose one thing to reference. If we can reference sort of like some arbitrary pressure and potentially throw off the scale.
There is a relationship between this and the primary quantities that we chose in the previous approach. If you chose a different reference scale for pressure, then you would just end up with another dimensionless group that would pop out of this analysis.
Right, like,
and then you'd have to say something about that dimensionless group.
Okay, it's like you could say like
pressure, like using pressure like 200 megapascal or something that may not really be relevant to the problem.
Yeah, it depends. Yeah, that may not be relevant. That may not be as relevant to your problem. I mean, really, what's happening here when we choose the reference scales and the things that we're going to say are constants, like mu and rho, and actually g is here as well in this problem. Those together are like the variables that we considered in the previous example, right? So when we said that the drag force is a function of u, d, rho, and mu, right? We had 5 variables. Those are like the reference scales that we choose here are like take the place of those variables in this kind of an analysis. I have to maybe develop that a little further so it'll make more general sense, because I don't think this is landing. Yeah.
We're in R.
R. Oh yeah. So if we're considering it, this is just if we're considering it in cylindrical coordinates or something, then we would scale R. Yeah. So this would be radius. Yeah. Sorry about that. This would be radius if we're considering in spherical coordinates. Yep. I think your textbook goes through the general definition. I should get rid of that. Yeah.
So we selected our scalar right now.
Mhm. Yeah. I mean, yeah, and we're trying to use as few as we can, yeah, to describe the problem. We could impose a length scale T, and then we actually get another dimensionless group out of the problem, which is something I want to hit on, but I want to think about it before I present it to the class, because there is a relationship between these two methods that we're getting at here.
So ambiguity, the dark arts.
Yeah, there's definitely a lot of dark arts here. So let's go through and apply this now. So we're going to start with incompressible continuity, right? So we have del dot v is equal to 0, or in Cartesian, du dx plus dv dy plus dw dz is equal to 0. And now we're going to go through and we're going to replace each one of those variables with their dimensionless counterparts. So we are going to, so we said that, for example, u star is equal to u, little u over big U, right? So that means we can rearrange that and say that little u is equal to big U, right? The reference scale times u star, the dimensionless form. So we can take that, our expression, our definition of u star, rearrange it and plug in, substitute in for the dimensional form of that little u. And we do that for every variable in the problem. Right, so we do that for all the velocities. Again, noting that we're using the same reference scale for all the components of velocity. And we do that for all lengths, right? We did the same thing, right? We said x star is equal to x over L. And so we can rearrange that and solve x is equal to L times x star. So that's where this came from. We also, on the previous slide said that we can, think about or write out a dimensionless form of the, of our del operator, right? So we can actually do the same dimensionless analysis in terms of this, del operator, the vector equation in kind of compact form. We'll see that we're going to get to the same place. So this is just going to be the two kind of side-by-side derivations coming down, hopefully to the same place. So then what we do with this expression is we're going to then gather out all of our dimensional terms. So we're going to take through, in this case, we're going to pull out the U and the L, right, out of each one of these things, right? Because these things are, for a given problem, U and L are going to be constant. So we can pull them out of all the derivatives. And those ULs would pull out in the front of each term, and then we're going to gather it all together. So we end up with U over L times this thing, where everything inside these parentheses is dimensionless, right? These are all scaled by the reference length scale. This is the equivalent in vector form. And now if we note that because we have this leading coefficient here, we can just divide through by this, and we're left with this expression for continuity, for a dimensionless form of continuity, right? Where it's u star over x star plus dv star over y star plus dw star dz star is equal to 0. So in this case, note that all the dimensional constants divided out, right? So we kind of got a little lucky on this one. We didn't end up with any new pi groups from this analysis. And we ended up with a dimensionless form of the continuity equation that doesn't have any coefficients involving those variables that are left. In a sense, we got lucky here. This does not always happen, okay? But in continuity, it does. So this is the dimensionless form of the continuity equation. Okay. So we're going to look at momentum, and we'll see that things are not going to work out quite the same way, right? We're going to end up with something left over. So we're going to do the same for momentum, and we're going to do this in vector form. So we're going to use our definition that del star is equal to L del, right? Which just comes from the fact that this del operator has length buried in it. And we're not going through it all in detail. If we apply this to Navier-Stokes momentum, we end up with this expression where so basically what we've done from this line to this line is take again, just do the same thing that we did in continuity. So take the definition of all of our dimensionless scaled variables, all our star variables, and plug those into, use those definitions to substitute for all of the dimensional forms of the variables that were in the original equation. So then we got some, you'd end up with some form of this expression with, a whole bunch of those constants floating around. And then by dividing through and rearranging those constants, we end up with this form of the expression. So what are the dimensions of this term? None. I heard none. Yeah, the dimensions of this term. There are no dimensions of this term, right? This is a dimensionless, right? Everything in here is dimensionless. What are the dimensionless of del star squared v star? Right, this is dimensionless. So what are the dimensions of this? Dimensionless. What is this? 1 over Reynolds number, right? So with dimensional analysis, Reynolds number pulls out of the Navier-Stokes equations. So this is another way of deriving where Reynolds number comes from. We can think of it as coming from the Navier-Stokes equations. Yeah, Michael.
So since in this situation, Reynolds number remains while it itself is one dimension, and it's not like the scalar values. Is that considered as the matters?
Yeah. Yeah, this is telling us that Reynolds number is the thing that we have to pay attention to, right? And this is why, early in class, I said, you don't really know much about the flow unless you understand what the Reynolds number is, because this Reynolds number really defines what's going on in this problem. And I see a mouth question of why, right? Are you saying why? Anyway, so we can think of Reynolds number as, and we're going to talk about this more as we talk about turbulence in the next chapter. But if we look at what's the terms in Reynolds number, we have rho UL over mu, right? Or inverse Reynolds number is mu over rho UL. So Reynolds number is rho UL over mu. This term here represents 1 over Reynolds number. This rho is the density of the fluid, right? And density times the velocity that's telling us something about the momentum of the fluid. So if we have a fluid parcel that's traveling through space at some given velocity, right, with some given density, this term here is telling us about the momentum of the fluid. And this mu, this tells us about the viscosity or the viscous drag that's occurring within the fluid. So if we have that fluid parcel moving through space, it's being slowed down by viscous drag against the other particles that it's encountering as it's moving through the fluid. And that's captured by mu, or really mu over L within the Reynolds number. And so Reynolds number is a ratio of the influence of momentum over the influence of viscosity within the fluid. So it tells us how important is fluid momentum relative to fluid viscosity. And so, for example, in what we can see from this expression here, right, this expression of Navier-Stokes, is that if, let's say, viscosity is really, really small, right? Let's say we have very, very little viscous drag within the fluid, or if viscosity goes all the way to zero, let's let viscosity go all the way to zero, then this term would drop out, which would pull out this whole term here. What we're left with is actually the Euler equations, which we said were equations of motion for an inviscid fluid. Alternatively, we could take this expression and we can multiply through by Reynolds number, right? So we could take we can multiply through by Reynolds number, and we'll end up with a factor of Reynolds number here, a factor of Reynolds number here. We'll get a factor of Reynolds number here, but pressure is a little bit weird. We'll talk about that in a second. But let's say we're going to have a leading factor of Reynolds number out here, right? If we multiply through by Reynolds number, this would disappear, and we get Reynolds number times everything else. And then if that Reynolds number is really, really small, which is what we call creeping flow, and we'll see some nice video examples of this in the coming weeks, then these terms drop out. And again, we're left with a simplified form of the equations. So just like Knudsen number, right, is the ratio of intermolecular spacing over length scale of the problem. So it tells us whether or not we can ignore the influence of the spacing between molecules. Reynolds number is a ratio of momentum over viscosity. And it tells us whether we can ignore the influence of viscosity or the influence of fluid momentum, which is here. Okay. Yeah, so we're left with a constant. This constant is dimensionless, and it's Reynolds number. I probably should have gone here for definition of Reynolds number on my next slide. So it's the influence of momentum relative to the influence of viscosity, right? Rho u, right, that tells us about momentum of a fluid parcel. Mu over L tells us about the viscous effects, the viscous drag on that fluid parcel. If we increase density, we increase the fluid momentum, and therefore we increase Reynolds number. Increase viscosity, then we increase viscous drag, right? Think about honey, and that decreases the Reynolds number. So since this was in our dimensional analysis of the Navier-Stokes equations, this was the constant that popped out. This is telling us, again, that if we want to understand what's happening in some kind of a problem in fluid mechanics, the first question you should have is, what is the Reynolds number? Okay. Because without the Reynolds number, you really don't understand much. So this is an example of, so this comes from the album of fluid motion. And we're looking at flow over just this square block cut out, right? So we have flow coming from left to right in both cases. So it's the same setup, right? This could have been done in the same, wind or probably water tunnel. So this could have been done with the same experimental apparatus. But in one case, we have a very low Reynolds number, and we see this like neat symmetry where it looks the same. If I were to flip this around, it actually looks pretty much exactly the same. And this is what happens at very, very low Reynolds number. Reynolds number basically going to zero, so we can ignore fluid momentum. So if we don't have the influence of fluid momentum, then we can end up with this nice symmetry in a flow problem. On the other hand, when we go to high Reynolds number, this could be same fluid, same setup, same lab, but we're just now at high Reynolds number. For example, we've turned up the velocity quite a bit. Then we transition to what's called turbulent flow, and now that symmetry is lost. Right? There's very different behavior in the front and the back of this block, and this is an entirely different, qualitatively entirely different flow than this was. So if someone asked you to say something like, what is the force on a block in cross flow, right? If you have flow coming over it, can you tell me something about what's going on in this flow? Like sketch streamlines or compute force, or estimate force or anything about this problem. But that same person who asked you this problem didn't tell you what the Reynolds number is. You'd have to say, well, I don't know. It depends, right? Because it could be something like this, right? The flow around a block in cross flow. Could be something like this. Could be something like this. Could be some other behavior that's not shown here. If you don't know the Reynolds number, you really don't know what's going on in a fluid mechanics problem. Yeah. Yeah. So in this case, I would probably choose L like this, right? That'd be what I would choose as L. I would choose U as the velocity, far away from the block, probably. Mu and rho would just be the fluid properties. But if you let's say this, I say they're the same. This one is probably a rectangle and this one's really a square, right? So maybe they weren't the same lab. But if in this case, if you chose this as L or this as L, right? In either case, you're going to get a big number for Reynolds number. This might be 10 to the 6th or something, like 1 million. This is Reynolds number of probably 0.1. Okay. So there's 7 orders of magnitude separating these two things from each other, right? These two flows from each other. So if you choose, this length, which is twice as big as this length to compute your Reynolds number, that doesn't matter too much. Okay. Yeah, question. So yeah, so in order to get to that Reynolds number, that equation that has Reynolds number in it, sorry, are you saying how we got to the expression with the 1 over Reynolds number, or when we multiply through by Reynolds number? The result is still dimensionless. Yeah, so the goal is not necessarily, so once we have it dimensionless, if we divide through by a dimensionless number, like we divide through by Reynolds number, it doesn't change the fact that every term is still dimensionless. And that's still, but it's still valid. It's still something that we can do to the equation. Originally, it was not dimensionless. Yeah, so to get there, we had to go through just like we did for continuity, and multiply, divide every term by the same dimensional parameters in order to have that dimensionless parameter come out. Yeah, good question. Other questions? Okay. Oh, yeah. Mm-hmm.
So if we just have a pipe with nothing in it,
Mm-hmm.
but then if you put something in it, like
Yeah, so the question is how do you choose? Let's say you have a pipe, you just choose the diameter of the pipe, but now if you have a little square block in the pipe, what would you choose? It kind of depends on what you're interested in. So if you're interested in flow around this little square object, then you should choose something related to the length of this square object. If you're interested in flow in the big pipe and this is just like roughness at the wall, then you should probably choose the length of the big pipe. Okay. Yeah.
We chose like the
diameter of the pipe. I'm not sure if it's going to be turbulent or not.
Yeah, so the question is, if you chose length as the diameter of the pipe and you weren't sure if it was going to be turbulent or not, which is definitely something that's going to come up, but how we determine whether something is laminar or turbulent. Could you change the length scale to decide? Well, if you, let's just go to this example here, okay? Let's say you choose this length scale, right? The height of this block, and you get a number that is in what we're going to define as the transitional region, where it is neither really laminar nor really turbulent, is what you get as your Reynolds number. And you say, oh, all right, well, there's another length scale. Let's use this one. It's twice as big. And now you get something that is at the beginning of the turbulent region, right? For what you estimate for Reynolds number. Does that change anything about what's going on? It doesn't change anything about what's going on. So the flow is still the same. And in both cases, you're probably around this transitional region. And where it's kind of hard to say if it's laminar or turbulent. So changing length scales doesn't let you, or changing the length scale that you choose doesn't change anything about the problem. And so it doesn't, it's generally not something you're gonna do, like change length scales just to learn, try to learn something else about the problem. Yeah, Paula.
Let's say I have a cube submerged in a fluid. The Reynolds number is no, what does that actually mean?
Yeah, so if the Reynolds number is what? Reynolds number is what? Sorry. Sure. Yeah, so right now we're just defining Reynolds number, and we've just derived Reynolds number from Navier-Stokes. In chapter 6, right? So the first thing we're going to do after fall break is start talking about really. One of the things we're going to discuss is how to use that to understand flow within pipes. And in chapter 7, we're going to talk about how to use that to understand flow around objects. Okay. So we don't really have all the tools yet to really say what's going to happen to this block on the basis of Reynolds number. All we know so far, right? Just to bring it back a step, all we know is that Reynolds number is important. And that's what I want you to take away from this. Reynolds number is important. Okay, you need to, in a fluid mechanics context, you need to understand what the Reynolds number is to understand the flow. Static electricity, there we go. This is going to get worse as it gets cooler and drier. Okay, so we're going to end by just discussing the fact that Reynolds number is not the only dimensionless number, right? It may be our favorite in this class, but it is not the only dimensionless number. There are a large number of other parameters, some of which are summarized in this table in your text that come out of all kinds of different physical situations. Reynolds number up at the top there because it's a fluid mechanics textbook. But there are quite a few others. The Froude number we're going to talk about when we talk about scaling, model scaling. It's like inertia over gravity. So all of these dimensionless numbers now we can think of as being the ratio of one thing to another, right? Like Knudsen was ratio of intermolecular spacing to length scale. Reynolds number is inertia over viscosity. All of these other numbers, right, including ones that you might recognize from heat transfer, we can think of them all as the ratio of one thing over another, telling us how important one thing is relative to another within a given problem. All right, so we'll end here, and this time the next class actually is Friday. We'll look at videos and we'll pick up on some model analysis. All right, thank you all.